Hello students and welcome to a new lecture about the mixtures of gases. We're going to be addressing Dalton's law, and in Dalton's law we look at a mixture of gases and we identify that each particle of the gas acts independently. So it doesn't matter if you have another gas with nitrogen, for example, nitrogen will react independently of that other gas. The partial pressure is the pressure exerted by a gas in a mixture. So if I have more than one gas in a mixture, each one of them will have its own pressure. And I'm going to call each one of those partial pressures. So the pressure of nitrogen is the partial pressure of nitrogen and so on. It will be the same pressure that the gas would have exerted if it happened to be alone. So nitrogen will have the exact same pressure even if it was all by itself. Dalton's law of partial pressure stating that the total pressure of mixture of gases is the sum of the partial pressures. Meaning if I have three gases, the total pressure will be the partial pressure of gas 1 plus the partial pressure of gas 2 plus the partial pressure of gas 3, as showing here in this equation. So Dalton pressure here, if I have gas 1 and it has a pressure of 1 atmosphere, and gas 2 alone has a pressure of 1.67 atmosphere, if I combine them and I keep volume and temperature constant, then the total pressure will be adding them together, and that will be 2.67 atmosphere. If you have a mixture of two gases only, A and B, remember, the pressure of A can be calculated by nRT over V, where N is number of moles of A. And the pressure of B is, this time, the moles of B. So, the total pressure, as long as I'm having the same temperature and volume, will be adding the total moles times RT over V. We also can get around this here by calculating what we call the mole fraction. So the mole fraction of I is number of moles of I divided by total number of moles. So the mole fraction of A is moles of A divided by total number of moles. And the mole fractions of B is moles of B divided by total number of moles. If you only have two components, then the mole fraction of A plus the mole fraction of B will equal 1. So the pressure of I will be the mole fraction of I times the total pressure. In our situation, the partial pressure of A equals the mole fraction of A times the total pressure, and the partial pressure of B equals the mole fraction of B times the total pressure. Here is a question. A sample has a natural gas has 8.24 moles of methane, 0.421 moles of ethane, and 0.116 moles of propane. If the total pressure of the gas is 1.37, what is the partial pressure of propane? So I'm going to show you the setup and you can actually finish the math because this is a really simple question. The partial pressure of propane, which is what they are asking, equals to the mole fraction of propane times, oh sorry, that is a mistake here. I meant to say the mole fraction of propane times the total pressure. Okay, so the setup will be, okay, then the partial pressure of propane equals, what is the mole fraction of propane? It is moles of propane divided by total moles in the mixtures times the total pressure. So the setup will be, what is the moles of propane? It's given as 0.116, and then down here you're going to add 8.24 plus 0.421 plus 0.116. And remember that mole fraction doesn't have units because you divide moles by moles. And then the total pressure is given as 1.37 atmosphere. So the answer will be in atmosphere. So this is multiplication and you get your answer. So this is one of the simplest laws actually to apply. This is here a way to collect gases in the lab. We call it collection over water. In this here, we are actually heating magnesium oxide. The outcome of that heating is to have an oxygen gas. This oxygen gas is going to come out underneath water, and then it will enter that bottle that initially was completely filled with water with no space. But once the gas starts to come up, it will push the water down and be collected over the surface of water. The reason why we mentioned that here, because that is also an application of Dalton's law. Because at the end of the day, we're going to have gas collected over water, So this is the water. So there will be gas molecules that are collected over water. However, there will also be water molecules that did escape the surface, and those water molecules also will be making a vapor pressure here. So they will also have their own partial pressure that we call vapor pressure. So the pressure of the oxygen will be the total pressure minus the vapor pressure, right? Because on top of water, there are two things: the water, the vapor pressure, and the oxygen itself. Okay, the vapor pressure does increase as I increase the temperature, because the more you heat the water, you give the molecules more kinetic energy, so they will be able to move faster, leave the surface, and become gas above the water and have a higher vapor pressure. If you look at this table, you will see that even at 0 degrees Celsius, there is a small amount of vapor pressure. That vapor pressure does increase as the temperature does increase. At the boiling point, which is 100 degrees Celsius, that vapor pressure is so large and equal to the atmospheric pressure. Now, let's using Dalton law here. So in those questions, I'm going to also focus on the setup. So 36 milliliter of a gas is collected over water. We are underlining water to remind you that vapor pressure has to be thought of at that point. And we are given the temperature, 25 degrees Celsius, and the atmospheric pressure, which is 757 millimeter mercury. How much oxygen is produced? I can know how much oxygen is produced if I have number of moles of oxygen. And I can get number of moles of oxygen if I apply the ideal gas law. I have volume and I have temperature. But the pressure that I have is not the pressure of oxygen, it's the pressure of water. So the first thing I need is to figure out the pressure of oxygen. So in order to do so, I have to have access to that table. And at 25 degrees Celsius, the vapor pressure is 23.76 millimeter mercury. So now when I go to solve the problem, the first thing I'm going to say is the pressure of oxygen equal to the atmospheric pressure minus the vapor pressure. And that will be 757 millimeter mercury minus 23.76 millimeter mercury. Now that I have the pressure of oxygen, then I calculate the moles of oxygen, and that is PV over RT. Now, P in this case, when you do your math, let's do this quickly, that will be 757 minus 23.76, and to keep my sig fig correctly, that will be 733 millimeter mercury. And the volume here is 0.036 liter. It has to be in liter. R is 62.4 millimeter mercury times liter over mole Kelvin. And temperature here you add, it's 298 Kelvin. That's going to give you numbers of moles of oxygen. Then the last step is to convert it into grams by saying there are 32 grams of oxygen for every 1 mole of oxygen. We have done this math a lot, so I'm sure you are comfortable with this. And you do the math, you multiply the number of moles by the molar mass, and you will get the mass of oxygen collected. Now, next question. Hydrogen gas is generated when calcium reacts with water. The hydrogen gas is collected over water at 30 degrees Celsius and 988 millimeter mercury pressure. The volume of the gas collected was 641 milliliter. What is the mass of hydrogen obtained? Same question as before, except that this time they actually gave you the water vapor pressure, so you don't have to go to the table. Okay? So same thing. You're going to start. I want you to solve this all by yourself. So I'm going to just give you the layout or the hints of how to do it. First, you need to figure out the pressure of hydrogen. You're going to have to subtract this from the total pressure. Okay? So that will be the total pressure minus the vapor pressure. Then you're going to have to find number of moles of hydrogen, and that will be PV over RT, where P is, remember, the pressure of hydrogen. You get P, they gave it to you. You have V, you have to convert that into liter. You do R, which is 62.4 because the pressure is in millimeter mercury. And the temperature, 30 degree, which you convert to Kelvin, it's 303 Kelvin. Once you have moles of hydrogen, now you want to figure out how much calcium reacted. You need to write the chemical balanced equation here of reacting calcium with water, which give you the metal hydroxide and hydrogen gas. And you have the same moles of hydrogen as the same moles of calcium. So you take moles of hydrogens, and then by 1-to-1 ratio, there is 1 mole of calcium for every mole of hydrogen. Then you multiply this by the atomic mass of calcium, which is 40.08 grams of calcium for every 1 mole of calcium, and you get the answer. Make sure you solve this all by yourself and use the discussion platform to compare your answers with your classmates. Next, we will be discussing the kinetic molecular theory of gases, which explains the behavior of gases that acts ideally. So, first, the volume of the particles is way smaller than space between them. Because remember, gases, it's almost empty space, right? That they are separated by large spaces. The particles are in constant random motions, and the collisions are perfectly elastic, and that which keeps the total kinetic energy constant. So means when the particle hits a surface, it bounces back and it keeps the same kinetic energy. Gas particles exert no forces on one another. They don't attract nor repel each other. That's ideal gas behavior. The average kinetic energy of the particle is proportional to temperature in Kelvin. So, at the same temperature, all gases have the same kinetic energy, right? So, this is very important, and a lot of students get here confused. All gases have same kinetic energy as long as it's the same temperature. Only temperature will change this kinetic energy. However, that doesn't mean they have the same speed. Why? Because kinetic energy depends on 2 things, the speed and the mass. So, they will have, the heavy ones will have lower speed, and the light one will have high speed. So, what they do have is similar average kinetic energy. Average kinetic energy, okay? Every word here matters. So the average kinetic energy for the particles is the same as long as I keep the same temperature. But they do have different speed, because speed, it will depends on the, you can't see this here. So we're saying that kinetic energy equal half mass square the speed, right? So kinetic energy, if the mass is large, then the speed will be small, like slow. And if the mass is small, which means light, then the speed will be high. So let's look at this distribution here. What we have a gas, and we are looking at, in the y-axis, how much, the amount of molecules with a certain speed. It's the same gas, I just changed the temperature. So when I have the blue curve, which is low temperature, the average here, because this is the amount fraction of particles at this speed. The amount, most of them are at lower speed. The red one, I have a high temperature, and the speed increases this way. So most of them are at a higher speed. So the average here, the lines here, the dashed lines, is the speed of the blue curve, the average speed of the blue curve, and the average speed of the red curve. And what I can notice that when I increase the temperature, the distribution does change. More particles at higher speed, and at low temperature, more particles at lower speed. At higher temperatures, we have more molecules moving faster, right? And at a lower temperature, we have more molecules moving slower. The next distribution here is I am at the same temperature, everything at 300 Kelvin. However, I have different molecules. I have a chlorine, I have nitrogen, and I have hydrogen. 3 different gases. The difference between them is in the molar mass. Chlorine is the heaviest, so most of it has what kind of a speed? Low speed. While helium is very light, so most of it at high speed. Okay, so again, the x-axis, again, is the same thing, guys. It's the molecular speed. So the root mean square, which is the speed, right, is directly proportional to the temperature. The speed will increase with increasing the temperature, and inversely related to the molar mass, the square root of the molar mass to be accurate, right? So the higher this one, which is the heavier, the lower the speed. Okay, so this is important, and we will use it in the next slide, as you will see. Diffusion is the gradual mixing of molecules of one gas with a molecule by another by the virtue of their kinetic properties. Diffusion, an example of diffusion, if I spray perfume at one corner of the room, somebody who is sitting at the opposite corner will know that I did so. Why? The gas diffused with the other molecules in the air till it reached the nose of the other person and did bind to the receptor that causes you to smell it, right? And it normally moves from regions of higher concentration where I sprayed the perfume initially, this is where the perfume was concentrated, all the way to the other corner of the room where it has a lower concentration. The lighter the gas is, the faster it will diffuse than a heavier gas. Now, remember that R1 over R2 will be equal to the square root of the molar mass of 2 and the molar mass of 1. So where is that coming from? I'm going to remind you of this so it doesn't make any confusion. We said that R1 is the root square speed, right? That's the speed. We said that R is inversely related to the square root of molar mass, right? So if I put everything here as we used to do in the ideal gas law, that means it's equal constant over the square root of the molar mass. So now when I'm gonna put everything together, how would that gonna look like? It will be R1 square root of molar mass 1 equals constant. Now, which means that it's gonna look like R1 square root of molar mass 1 equals R2 square root of the molar mass 2. Now, let me put a line here. So now if you take this part and rearrange it to look as this one, it will be R1 over R2 equals the square root of molar mass 2 over the square root of molar mass 1. It's important that we can have it as a ratio because that's a speed ratio. So if gas 1 is 2 times faster than gas 2, that means that R1 over R2 equals 2. If gas 1 is 5 times faster than gas 2, then that ratio equals 5 and so on. Now, there is also the Graham's law of effusion. And effusion is different than diffusion because effusion is gas under pressure escapes into another area by passing through a small opening. So you have to have a small opening. And the effusion of mixture of two gases will follow the exact same ratio here, where R1 over R2 will equal the square root of the molar mass 2 over molar mass 1. Meaning, the heavier the gas is, the slower it will be, and the lighter the gas is, the faster it will go through that opening. Here is an example to apply what we just learned. If carbon monoxide gas effuses as a rate that is 1.48 times of an unknown gas under the same experimental condition, what is the molar mass of an unknown gas? Okay, let's see what we have here. We know R1 over R2 equals square root of molar mass 2 over the square root of molar mass 1. If I called 1 to be the carbon monoxide gas, then R2 will be the unknown, right? Now, they're saying that the rate of carbon monoxide effusion is 1.48 times faster, which means the whole ratio is equal 1.48, right? This is the ratio of the speed. So then 1.48 equals 2 is the unknown, the square root of the unknown, and then this will be the square root of my known, which is carbon monoxide. 14 plus 16, that is 30. That's the square root of 30. So now let's do the math. The square root of my unknown equals to 1.48 times the square root of 30. And that equals to, if I do the square root of 30, times 1.48, that equals to 8.11. Now that means, if I want to know now, that means that the molar mass of the unknown equals 65.7 gram per mole. Now, it's important that you recognize in this case, they gave you the ratio. Sometimes they're going to give you the speed of both. And for the effusion speed, effusion is normally given as volume over time, right? So the effusion is like going to tell you 3 liters passed in 60 seconds. That means if R will equal 3 liter over 60 seconds. So pay attention if they are giving you a ratio, which is the whole thing, R1 over R2, or if they're going to give you different R's individually, which means volume over time. Now, difference between ideal gas and real gas. Ideal gas will occur when there are no interactions between the particles, so whatever, and specifically attraction. And that can be achieved if I have high temperature. High temperature will make them get away from each other because they are moving so fast, and low pressure so they don't get to be compressed, right? That is not, we don't want that in ideal gas. So if I tell you which of the following conditions are best to guarantee ideal behavior, it will be the condition that will give me minimum interaction, minimum or no interaction at best, right? And that will be high temperature and low pressure. In the opposite circumstances, if I have high pressure, they're going to come close to each other. And if I have low temperature, they're also going to come close to each other. So this is when it's non-ideal behavior. This is all for this chapter. Thank you very much, and I will see you in the next one.